My name is Eben. I will be the chair for this session. And we have three presenters, two in Perth and then one in, I think, Hobart. So the first presenter and one will be talking on automating workflows and the benefits of working as a data analyst within a clinical research team. Thank you.
Alrighty. So I'm Anwen Taplin. I'm from the Kids Research Institute Australia, and I work with the anaesthesia research team at PCH. So today I'll be talking about automating workflows and the benefits of working as a data analyst within a clinical research team. So first, this is our studies. Not really. So as Daisy pointed out this morning, we work at Perth Children's Hospital, and every study we have a convoluted name, which is normally to do with an animal, and then we'll get a soft toy for that animal to encourage the kids to come and join in our projects. So on to what our team actually does. We're obviously the anaesthesia research team. So our main aim is looking at making anaesthesia safer for kids, but we also look at a lot of other areas, as is on this diagram. So there's things like trying to reduce anxiety, trying to make kids more comfortable when they have to come into hospital for a procedure, trying to reduce their pain after they've been in hospital, and also just a whole bunch of other things to do with surgery. Like I worked on a project with lung mechanics, which I didn't understand a lot of it because I don't have a background with that, but very interesting stuff. So my topic today kind of bridges a lot of these projects because I'm talking about the data processing and how we get data into a stage where we can actually analyze it to get the outcome of these projects. So when we have a study, we're collecting data from a whole bunch of different areas. A lot of the time, at least in the past, a lot of the places we were collecting the data was on a paper record. So we would have a data sheet. The research assistants would go out to a family before they went into surgery, and they'd be circling, did you have a cold in the last 2 weeks? Do you have a smoker in your home? Do you, what surgery are you coming in for? What was your date of birth? And they'd be writing it all on this data sheet. And then they'd have to come in and type it into our database so that we can export it and analyze it. And obviously that's a bit time consuming. So the aim is to try to get everything into that database before then. The other ways that we can get our data, so some things we don't have to actually ask the patients or their family. We can go behind the scenes and get the digital medical records with their medication lists or how long they were in surgery for, what time did they go in, what time did they come out. And then the third kind of data that we use as a team is if we put some sort of device or monitor on a kid to measure, say, their oxygen to see how many desaturations they have, or we might put them into a sleep study before they come in for surgery, and then we'll get a whole bunch of things like they have sleep apnea or they had this many desaturations overnight. So that kind of information comes to us in a report exported from the monitors, and the research assistants have to copy the information that we care about into the database so that we can use it when we do our analysis. So obviously, I'm sure you can all think of some drawbacks of just copying this data between places, but I'm just going to go through a few quickly. Main one is it's very time consuming, but we're also going to get these random human errors where you've missed a decimal point, you just typed a number wrong. And also the third one, which I've come across in this job, is that sometimes people will do their calculation outside of the spreadsheet. Like they might be calculating BMI and they'll do it on their calculator and then put the answer in. But if they make a mistake, that's not tracked anywhere. And we might see a BMI which looks normal on its own, but when you look at the age of the patient or some other factor, you'll see that doesn't make any sense. And we can't track what the original value was anymore because it's just been lost in that spreadsheet. So sometimes you get given these spreadsheets, which essentially come from a kind of black box, and we don't know if we can recover the data necessarily, and if we do, it's going to be really time consuming. So not ideal. What we did, we just wrote a script that would take output from monitors, collect the values that we want, and put it into a spreadsheet. So normally it's in this very standard format. So I've put some output here where we've just got desaturations from an oxygen monitor. And you'll have a file like this for every patient in your study. And instead of having someone go in, open up the file, take the number that you want, we've just got our script to go to line 4, take the second number in that row, put it into the spreadsheet. And it's way quicker. And it's a lot better for us when we get the spreadsheet because we can tell exactly where the numbers are coming from. And I've added in this data checking point to the flowchart because that time that we've saved from our research assistants manually copying the information across, they can now use that time to check that the numbers actually make sense. So you might have a monitor that fell off of the patient overnight. And it's very obvious for a research assistant to see if that's happened. It makes no sense to me. I'll have no idea. But the research assistants can spend the time, instead of moving data to different places, they can look at it and go, let's just completely exclude this thing because it makes no sense. The monitor clearly fell off. So we've turned this black box flowchart into something that's documented. Someone else can come into the team. If something gets updated, we want a new value from those reports, they can just add it in. Very quick, very easy. Everyone knows where the number is coming from. Everyone knows if the calculation is being done with the number and what the calculation is. So in the last few minutes, I hope that I've got, I wanted to talk about why it was so easy for us to do this is because we're actually embedded within the clinical research team instead of being situated outside. So we're involved when protocols are written up, we're involved in making the databases that are used, and we're involved in the analysis and writing after a project has all of the data has been collected. So because we're embedded in the team, we could see that this process was very time consuming and inefficient, and we could improve it before the data had finished being collected and update the process early. And also, so because we're embedded in the team, if someone comes to us later and says, actually, we have the number of desaturations, but we also want the average time of desaturations, we can go in and update that very quickly, rerun the script, it's all done. I think that brings me, oh, do I have more time? Yeah? Okay, if I've got more time, back to the original flowchart I had at the beginning, I just wanted to say that even though I'm working within one team, I get to work on heaps of different projects. So I work on some projects that are just a simple analysis and maybe it's more of the write-up stage. But I'm also working on projects that are like really computational and more modeling, and like I'm learning new statistical techniques that I wouldn't have learned just in a uni course. I get to learn it on the job. So I've put a little star next to all of the projects that I've worked on while I've been in the team. And it's like, you can see it's across a lot of the arms of the chart, which I just think is pretty cool. All right, acknowledging my team. And if you have any thing you want to talk to me, feel free to email.
Thank you very much, Anwan, for sticking to the time. The next presenter, Prince, is presenting on a trend cycle analysis of the evolutionary trajectory of Australian housing prices.
Thank you. Once I've already been introduced, I will just go straight ahead and do my presentation. It's more like an exploratory study as part of my PhD project, and the list on the left down consumer supervisory team. I guess you all know that housing is quite important in one's life, whether you are a homeowner or a renter, and also important to the economy as it plays a crucial role in looking at the financial systems as well as contributing significantly to household wealth. And any shock in the housing market can have some sort of devastating effect on the financial systems, as well as undermining the financial security of household as well. And one of the key metrics when it comes to housing market performance measure is housing prices. Simply because when the market is performing or underperforming, what comes to people's mind is simply, what are the prices faring in the market? That's what comes to people's mind. So because of that, analyzing the long-term trend in the cyclical pattern of housing prices is quite essential to economic forecasting as well as policy decision making, because these prices usually influence consumer wealth and then spending as well. So a lot of studies have been undertaken focusing on analyzing this trend and cycle component of housing prices, usually in the time and frequency, either time domain or frequency domain. But set techniques usually attribute the underlying dynamics to the whole study period. But meanwhile, housing price is a non-stationary process, and its behavior doesn't remain constant over time. And then also focusing the analysis on only frequency domain can also ignore time-varying information of these prices, leading to transient relationships and structural breaks pass undetected. So analyzing these components in both time and frequency domain using wavelet transform techniques can actually help addressing these kind of challenges. Thus, this technique can preserve time information as well as distinguishing long-term trend from cyclical patterns. It can also preserve or provide more nuanced understanding of the underlying dynamics, and also can handle non-stationary processes, because the technique is quite non-parametric. So it doesn't make any distributional assumption about the process being investigated. And it is also compactly supported. That is enabling temporal localization of the processes characteristics. So with these capabilities and using continuous wave transform methods, we seek to address questions relating to the extent of housing price instability over the period. Also, the degree of joint movement among the housing prices of 8 capital cities for Australia, and then also the identification of leading or lagging cities in a multivariate relationship. So with this, we used median housing prices of Australian capital cities observed at quarterly time points, and these represent past transactions of houses, and the period spans March 1980 to June 2023. And we saw this data from Real Estate Institute of Australia. So the figure on the left-hand side depicts the movement in these prices over time. So here I don't present or I've not provided the mathematics behind the method that I'm using, because for the purpose of this conference, but I'll just briefly talk about them. So the continuous event transform technique usually will transform time series. So for example, here the housing prices, which in time dimension into both time and frequency a domain. And based on this transformation, you are able to estimate some functionalities such as wavelet power spectrum, which will determine the variation in these prices for both time and frequency. And also estimate wavelet coherence, which will also determine the interdependencies among these prices of the cities, and then phase differences, which also help us to identify the most dominant or leading city in the pairwise or multivariate relationship. But this technique usually provides information about interdependencies in different segments in time, with leading and lagging roles alternating. So because of that, we are not able to determine the eventual leading or dominant city in the pairwise relationship. So because of that, we also employ transfer entropy technique as a complementary approach. And this technique can quantify information flow between two processes or time series. And because information transfer is asymmetric, this technique can quantify the bidirectional flow of information and can also determine net information output. So because with that one, we're able to identify the eventual leading or dominant city in the multivariate or pairwise relationship. So some results. So first, I'll show the wavelength power spectrum results. So I have 8 of such figures, one corresponding to ECT, that's the power spectrum, where I show Sydney for the purpose of this conference, but I'll talk about the ACTs as well. So here, the vertical axis represents the scale or period in quarters, while the horizontal axis represents time in calendar dates. And more red the color, the higher the variability in the prices. And then the more blue, the lower the variability in these prices. So here we found that all the ACTs exhibited higher variability in prices between the mid-1980 and 1990. And in the short run, that's corresponding to scale up to 4 quarters. And this development reflected the major housing cycle in the late 80s, which peaked in 1989. We also observed that these cities exhibited lower variability in prices in the long run. That is corresponding to scales from 8 to 2 quarters. And this shows that prices over a long period were relatively stable. We also observed keenly 3 distinct periodic bands corresponding to short-term, medium, and then long-term variabilities in these prices. And this also suggests that in analyzing these markets, one needs to adopt a multi-scale approach to be able to come out to a valid conclusion. We also present wavelength coherence results. So here too, I have 28 of such pairs, each corresponding to a pair of cities. So here I show Sydney and Melbourne, but I'll talk about Sydney and its pairs for this presentation. So here too, the more red the color, the higher the coherence, and then more blue, and the lower the coherence or even no coherence at all. So here the arrows, when it points to right and tilts down, it means that the first city in the pair leads the relationship. When it tilts upwards, the second city leads. And when it points to the left, then it means that the cities move in opposite direction. So here, with Sydney and its pairs, we found that Sydney influenced its pairs in a short run. That is case up to 4 quarters, but it was rather influenced in the long run. So we found that leading and lagging rules alternated between Sydney and its pairs. And similar observations could be made for other pairings. So with this strong coherence, this also highlights the potential local housing policy spillover effect. And in addressing issues pertaining to this market, this shouldn't be done in isolation, but rather conditions pertaining in other markets should be considered. I also present the transfer entropy results, which also quantify information flow between these cities. So on the figure A, depicts information exchange between the cities. So cities marked on the vertical sent information, whilst cities marked on the horizontal receive information. So when we find the difference between the total information sent by city and that it's received, then that translates into figure B, which depicts the net information outflow. So if the net information outflow is negative, then it means that that city influences its pairs when it comes to information sharing. And if it is negative, then that city is rather being influenced. So here we found Darwin, Melbourne, Perth, and Canberra to be influencing their pairs in terms of information exchange. Whilst Sydney and the rest also exhibited negative outflow. But Sydney is not surprising because we found from the coherence analysis that Sydney, as it influenced its pairs in the short run, it was rather influenced in the long run. So that resulted in the net negative outflow that we see here. So monitoring such dominant cities can also help to avert any potential spillover effect. So we have some implications and for policy and investment. So one, identification of the leading cities can also help policymakers to prioritize monitoring development in those leading cities in order to avert any potential spillover effect. And also identification of the periodic bands can also assist investors to time their investment, identifying optimal entry and exit point, whilst minimizing their returns in order to maximize their returns. And then also varying degree of lead-lag relationship can also provide diversification opportunities, because in our analysis, we found Melbourne to be exhibiting negative relationship, long-term relationship with its pairs. And because of that, investor can take advantage of these segmented markets and maximize their returns. So these are references, and then acknowledge my School of Science, ECU, Mother Group, and then Masover's panel for their wonderful support. Thank you.